at home, here comes your warm-up. Yay! This one. Find the missing side length or edge length of the squares or cubes below. Round your answer to the nearest thousandth if necessary, and write the exact reduced roots if you can. Alrighty, everybody. Those of you at home, you might want to pause this in just a moment. Can I get you guys back up here in 5, 4, 3, 2, 1? Let's go ahead and talk about this, guys. So, I want to do number 3 and a number 2. Number 3 and number 2. So, let's see here. On number 2, what are you going to do to 54 to find out what that's going to be? Solomon, what am I going to do to 54 to find out what the edge length of that cube is?
You're gonna find out the cube of 54.
That's exactly right. We need to take the third root of 54. So if I grab my handy-dandy calculator and I say, hey, calculator, what's the third root of 54? It's going to give you a big, nasty, approximate answer, 3.7797, which would make it about 3.78. 3.78. So the edge length is about 3.78 feet. And the reason that is because 3.78 to the third power, that is multiplied 3 times, is going to get me a number that's pretty darn close to 54. Depending on what we're trying to accomplish, that might be close enough. Great. How many of us got about 3.78 for that one? Great. Common mistake I've been seeing on your skill check, by the way, is that people who put 3.780, because they're thinking rounding to the nearest thousandth, I actually want that 0. Decimals are not simplified if there's a 0 at the back, so we do not want that ending 0, okay? Not on a decimal. No, thanks. Only very rarely do we want those. It's like when we're talking about money, or if somebody demands that you do it to whatever significant figures. But anyway, that's more of a science thing. Let's go ahead and reduce that. So if I do the third root of 54, we make a 54 factor tree. 25, 27, and 3, nope, 2, 9 and 3, 3 and 3. So the third root of 2 times 3 times 3 times 3, I got a set of triplets. The 3's yoink out. 3 cube roots of 2. How many of us got 3 cube roots of 2 for the reduced root? Perfect. That's exactly what I would do as well. Now on this one, guys, this actually answers a question. Like, let's say that you were like, I'm going to get the exact first. So I'm going to do 1296. I'm going to start reducing that. I can reduce that by 4, I think. Let's see, 1296 divided by 4. Nope, that's not that one. That's not the one I want. Although I think that is also divisible by 4, funnily enough. That's 324 times 4. That's 2 and 2. That's divisible by 4 again. Which is 81 divided by 4. That's 9 and 9. That's 3 and 3. That's 3 and 3. That's 2 and 2. So this becomes the second root of 2 times 2 times 2 times 2 times 3 times 3 times 3 times 3. I see a pair of 2's. I see a pair of 2's. I see a pair of 3's. I see a pair of 3's. Uh-oh. And this often asks, like, what does that leave in there, right? Like, once everything's gone, what's left in there? And the truth is, guys, there's nothing left. But if you really want to think of there being something, I guess you could say it's times 1. And then, so we have 3 times 3 is 9, times 2 is 18, times 2 is 36. 36 square roots of 1. But what's the square root of 1, everybody? 1. What's 36 times 1? It's 36. 36. That's okay. Hey, it's okay. Happens all the time. Happens all the time. 36 inches. Now, guys, these numbers are very different numbers. Like 36 and 3 cube roots of 2. Those are both exact lengths for these last 4 lengths, but they're very different numbers, and today we're going to talk about in what way they are different. Will you guys go ahead and open up your... it's the 56th day of school. What am I saying? In 1941, Joe DiMaggio recorded at least one hit in 56, and I need to say consecutive games, like 56 games in a row, which is considered one of the most unbreakable records in sports. I have a question for you. If you're a big baseball fan, maybe you can help me. Because here's the thing, is that in my mind, if a basketball player did not make a basket in an entire game, that would be really bad. Am I wrong? Like, if there's a person who is like, and Joe DiMaggio is one of the greatest of all time. Like, if your best player didn't make a basket in the entire game, that would be really bad, right?
Yeah.
So I'm curious, why is this so unbreakable? Why is just getting a hit, not even getting a run, just getting a hit in 56 games in a row? Why is that so amazing, Jack? Because I don't know.
Well, I was about to say in basketball, the lowest amount of points LeBron James has ever gotten is 3,
Yeah.
which is amazing.
I know, and so like to me, that means like, and I mean, what happened? That means to me that he never has scored 0 points, which means he scored in like 300 consecutive games. Do you know what I mean? So I don't know why this is so much of a why that seems so unbreakable. Yeah.
Well, yeah, because in baseball, usually you get 4 at-bats,
Yes.
or 4 and 3. So, usually an average is like, a good average would be a 245. So
So you're saying 250.
yeah.
So I was about to ask you. So average batting is 250.
That would be pretty good for
That's really good.
yeah, that's pretty good.
That's really good. Like that makes sense then because if you get 4 at bats and 250 batting average is good, that means the average people get a hit every time, maybe multiple hits one day, maybe 0 hits a different day. That's wild. Baseball's crazy, man. Baseball's crazy. I love it. That actually helps a ton. Thank you so much. In fact, Jack, that helps so much. I'm going to put you on the start team because I have that is the first explanation that I have found satisfying. Andre. That's terrible. That's terrible. Yeah.
In the World Series, did you snap shows? Jose Altuve went like 0 for 21 in the first 2 series.
Yeah.
In the World Series, I think he hit like almost 300.
That's amazing. That's amazing. Good. You got it where it counts. Hey, it's National Seatbelt Day. Yay! I don't know about you guys, but if I'm in a car and I'm not wearing a seatbelt, I pretty much feel naked. Do you guys know what I'm talking about? Like, as soon as I'm in, I gotta buckle that seatbelt. Like, if people start, like, they could just be backing out of the garage and they'll be like, "Whoa, stop the car! I'm not buckled in." How many of us are exactly like that? I am too. I am too. I can't deal with it. I can't deal with it.
If it gets in an accident, I don't want to be in the car anyways.
Well, you don't want to get ejected into traffic.
Well, I'd rather that than be in the car when it's dead. If it's on fire, why would I want to stay in the car?
I'm gonna go ahead and I'm gonna go out on a limb that that most of the time when cars crash, they don't catch on fire.
Well, what if I just like drove in straight water and I have to spend the extra 10 seconds taking my seatbelt off?
So I think one of the problems is that we're thinking too much of movie accidents, which have to be exciting, so you're in the water. I have a feeling most accidents involve another car and you just hit it, and then if you're wearing your seatbelt, you walk out. But if you're not wearing it, you just get flung out at 65 miles an hour, which I can tell you is not going to work out so hot. I'm telling guys, I don't think I'm being controversial when I'm saying, you guys, wearing a seatbelt is safer than not wearing a seatbelt. Guys, I have a feeling this is going to become a debate that we don't have time for. So, what is our first essential question? And trust me, you want to get to these essential questions today, especially if you saw the second one. Let's see here. Let's go for it. Jack, what's our first essential question? What is the difference between rational and irrational numbers? And our second essential question, I would love to get that one from, let's go for it. Peyton, what's our second essential question?
How did that thingy get someone killed?
How did the square root of 2 get someone killed? How did the square root of 2 get somebody killed? Let's see here, guys. Where is that? There we go. Here we go. Okay. Voice is off in 5, 4, 3, 2, 1. Hey, our Jeopardy this week is U.S. states. Becoming a state in 1850, the 31st state is the third largest in size and the largest in population. Let's go ahead and put the cubes away, guys. That is indeed California. California is correct. And then, and then footwear. Oh, I don't see it. Nope. Nope. I think I heard it. Shoes. It's just shoes. Just shoes straight up. Shoes straight up. Okay. Can I get you in 5? You got. It's okay. I think you were overthinking it. That's all right. 4, 3, 2, 1. Got a pencil? Today we're talking about irrational numbers. Irrational versus irrational versus rational numbers. Here's what's going on here, guys. Maybe I should explain this. There was a time. This was a long time ago. I don't. It's the BCE, right? Like it's before our AD. So I think maybe, if I had to take a guess, I want to say it was like 900 BC, right? 900 to 600 BC. Long time ago. There was a group of people that we'll talk a whole lot more about in February. But for now, we're just going to kind of touch on them. And one of the things that they believed was that that every number could be represented as a fraction of integers. That they said there must be a number that represents this as a fraction of integers. Makes sense to me, right? I mean, why not? It's kind of like this. 4.7. How I can represent that as a fraction of integers. How did your angry elementary teachers force you to say that? If you were like, teacher, that's 4.7, and they were like, wrong! Don't you say 4.7 in my classroom, you little... What was the ba-ba-ba-ba-ba? That was the ba-ba-ba-ba-ba. So, it's recorded. It's a ba-ba-ba-ba-ba-ba. How did your rage-filled elementary teacher force you to say that at risk of a beating, Trace? 4 7/10. 4 7/10. It's okay. Now, that's still not a fraction of integers, but I can make it a fraction of integers really easily. Saying 4 times 10 is 40. That's 47/10. That's okay. We're not actually doing all this. I'm just proving a point. That this right here is a fraction of integers that represents that situation, right? So that means that this number, this is how they would have done it. They would have said, I can say any number as a fraction of integers. Look, there's 4.7, and now it's 47/10. And everyone would clap and say, hooray, you've done it. Good show. Now, this gets a little bit weird with repeating decimals. Got a pencil? 0.21 repeating, for example. Because here's what I ask elementary teachers who get super mad about the way you pronounce things. How do they pronounce that? 0.21 repeating. Yeah! How come that's okay? How come that's okay? And it's because that's not tenths. That's something else, which we're going to talk about right now. Now, we actually have a way to deal with this, and it involves algebra. We're going to set that equal to x. Is that okay? 0.21 repeating is equal to x. Now, the period of this repeating decimal is 2, because there's 2 decimals that repeat. Now, if this really did say this, how would your teacher make you say it? 21 hundredths. Now, that gives us the clue of what we need to multiply both sides by, 100 and 100. I know that might seem very mysterious right now, but trust me, it's going to make sense. You move the decimal over twice. That becomes 21.21 repeating equals 100x. Are you guys okay so far? I mean, that's a weird thing to do. Like, maybe you're like, why did you do that? But I'll show you why, and there's actually a really nice shortcut to this. So, yeah, but unfortunately, that's not an integer, right? So I haven't proven that I can write an integer yet. But here's what I am going to do. I'm going to subtract x from this side. What's 100 minus x? 99x. But guys, didn't I just say that x was 0.21 repeating? Yeah! So if I have 21.212121 infinity, and I subtract it by 0.212121 on infinitely, what happens to all these numbers? They go bye-bye. So 21 equals 99x. I divide both sides by 99. And I get x was 21/99ths that whole time. Right? Right? Yeah, and we can simplify that to 7/33, but actually, simplification was beside the point to these people. What they wanted to say was that a number, every number can be written as a fraction of integers. Every number can be written as a fraction of integers. That's what they said, and once they did it, they were done. This actually led to the very interesting discovery that this is true. 0.9 repeating. Well, let's see why. 0.9 repeating is A. How would your teacher make you say that if that weren't there? 0 and 9/10. So we're going to multiply both sides by 10. What's this? 9.9 repeating equals 10A. Now we're going to subtract A from both sides. But over here, that was 0.9 repeating. So all those 9s will be gone. So 9 equals 9A. Divide both sides by 9. Sorry, it's 1. 0.9 repeating is 1. It's 1. Oh, I already, yeah, it is 1. And if you feel that makes you really uncomfortable, I'll tell you what, I'll concede that the 0.9 repeating is not 1 as soon as you tell me a number that exists between them. Oh no, 0.8 is less than 0.9. 0.9 repeating. Yeah. Oh no, because 0.99 is above 0.95. It's closer to 1. I need a number that's closer to 1 than 0.9 repeating. That's what you need to give me. If you can do that, then I'll concede. Frankie? 0.910. No way. 0.910 repeating? No way. No way. No way. Anyway, we could run around in circles with this all day as well, but maybe at the end of the day we can come back. Here's the point. This is the one that bothered them the very most. They kept scratching their chins and wondering, how do we come up with a fraction to represent the square root of 2? Because if you pop that in your calculator, the square root of 2, sure, but that's 1.414213562. I'm going to write that down. It's about 1.41421, about 1.414213562. Okay? And I know that some of us might grab our calculators and say, well, Mr. Petersen, that really works. Watch. We're going to do 1.414213562, and we're going to square it, and watch this. Oh. Great. No, because actually this, I know, if it was repeating, yes. But actually, if this was, I'll bet you what happened is that this last digit that we cannot see is actually, it couldn't be 8, because then it would round up to a 2. I'll bet it's like a 4 or something. Let's take a look. Let's take a look at Wolfram. Let's take a look at Wolfram and see what Wolfram has to say about the matter. I know, Wolfram's great. I love Wolfram. I got to blank the screen, though, to get there, because it's going to pull up everybody's grades if I don't. All right. It does. It does. Okay, here we go. Can I get some help? And I would like that from, that's going to be, Chris, can you tell me what that number was that we just squared? 1.41? Oh, no, so that's what it was. But what's what was the square root of 2? 1.414. Does someone have that? Did someone write that down? Let's see here. Go ahead, Trace. What was it? Whoa. 1.414215. 4142 13562. Look at this. Look at this. Like, this means that people on Wolfram have asked this a lot. Yeah, it was. Oh, Oh, actually, we got bamboozled. Oh wait, sorry. Those of you who are at home, I didn't unblake the screen. I'm so sorry. There you go. Yeah, except here's why it's a 9, guys. The calculator tried to cut it right here, but what came after that 8? So it rounded up. So we got hoodwinked. Yeah, so as you can see, guys, that's not actually 2. It's close. It's close enough, maybe. But here's what happened. The guy who ran this, I'm not going to lie, he was a brilliant mathematician, but he was also like a creepy cult leader. He was also like a creepy cult leader, like for reals. Like he worshipped numbers. And so one of his students named Hippasus proved that you cannot write the square root of 2 as a fraction of integers. Cannot be done. Well, yeah, but hold on. Don't get to the end of the story. Let me show you his proof. It looked like this. Got a pencil? So let's assume that the square root of 2 is equal to a fraction of integers, a over b. Now here's an important thing. A and b may or may not be reduced, so let's just assume that they're reduced, right? That means that a and b have no factors in common. Are you guys okay with that? That's how it goes. So now we're going to square both sides. Because the square root of 2 squared is 2. The square root of a over b squared is a squared divided by b squared. So somehow we had an unreduced fraction that when you multiplied this number by itself and this number by itself, divided out to 2. But that's not possible because do a and b have any factors in common? No. So it's impossible. And he went to his teacher with this, and the teacher looked at it and said, "Oh, Hippasus, pat, pat, pat. Don't worry, I'll find your mistake, and I think it will be a beautiful discussion tomorrow." And he went home, and he like, "Oh, that silly Hippasus." I, uh-oh. I can't prove him wrong, but I've built this whole cult over this thing. And so they went down to the meeting, and Hippasus was like, "What did you figure out?" And he was like, "That you're a heretic, and we're going to tie you to a chair and dump you in a river." And they did. 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 So, don't worry, guys. This creepy cult leader, who we'll talk a whole lot more about in February, do you guys think he made some enemies? Yeah, I'd say when you're drowning people in rivers because of math, you'll probably make some enemies. And I'll tell you right now, he gets his in the end, and his death, which we will go over in February, no kidding, absolutely true, 100%, has a lot to do with farts. It is absolutely true. It is absolutely true. Absolutely true. Now, let's talk. Here, we got to get through this and we'll get there. Got a pencil? Absolutely. A rational number is a number, duh, but a number that can be written as a fraction of integers. That a rational number is a number that can be written as a fraction of integers. If you can write it as like negative 17 over 2, that's a rational number. I wrote it as a fraction of integers, okay? A rational number is a number that can be written as a fraction of integers. Here's an interesting aside, is that because of that, any rational number has a decimal expansion, like when you write it as a decimal, that terminates, that is, it ends, or repeats. There's a really good reason for that, too. You can put your pencils down once you get that written. I just want to show you. There's a really good reason for that. that if I take 4 divided by 8, is that a fraction of integers? So is it rational? Yeah. Oh, by the way, negative 4 divided by 8. And when I do the division, like how many times does 8 go into 4? Well, it doesn't, so 0 point, it goes into 40, 5 times 5. 40, subtract, it's gone. Bam! So it's negative 0.5, right? It's got a decimal that ends. Now, here's the thing. I'll tell you guys right now, the number one mistake that people make on this is people assume that this is irrational. 12/17. Because does that decimal look like it ends?
No.
No. Does it look like it repeats? No, but it does. How are we supposed to know that? Well, think about the process here. How many times does 17 go into 12? It doesn't. You put a 0. 120. 17 goes into 128 times, was it? Let's see. What's 17 times 8? So we can try 17 times 8. That's too much. So 17 times 7. 17 times 7. That's 119. Oh, so close. And then you get a 1. It doesn't fit in there, so we have to do that. Still doesn't fit in there, so we have to do that. Add a 0. 17 goes into 105 times, right? So we do 17 times 5. Now, guys, this process might seem like it takes forever, but here's the funny thing. Every time I do this, I'm going to get a remainder. Will I eventually get the same remainder?
Yes.
I have to, right? There's only 17 possible remainders I can have. Well, sorry, 18. 17. 0, 1, 2, 3, 4, 5, 6, 7. I can't have any other amount of remainders. So eventually I'm going to get back to where I started, and eventually it's going to repeat. How long? Oh, well, from alpha. Let's see here. Well, from alpha, how long will it take 12/17 to repeat itself? Oh, good. It's 0.70588235294117764 repeating. It takes literally every possible step it could have to repeat. But it will repeat eventually. Any fraction of integers is guaranteed to be a repeating decimal or a terminating decimal. Or if you're feeling cheeky, they're all repeating because technically you're like, well, 8 goes into 0 0 times, and then 0, and then 0. It's a repeating decimal. 0.5, negative 0.50 repeating. Go for it. That's fine. Whatever. So they're all repeating or terminating. So there are numbers that are called irrational numbers. Got a pencil? Irrational numbers are numbers that cannot be written as a fraction of integers. Irrational numbers are numbers that cannot be written as a fraction of integers. That cannot be written as a fraction of integers. Of course, I heard someone actually mention another one. That's actually a little bit harder to prove than you might think. So a lot of people will actually fall back on this other reason that why that one's irrational. Andre, you have a question. Let's talk about it. So here's an interesting thing. If rational numbers are numbers that can be written as a fraction of integers, and so they have decimals that terminate or repeat, what do you think is true about the decimal expansions of irrational numbers? Teach! Okay. Can I get you back up here in 5, 4, 3, 2, 1? Shh. What do you think that means must be true about irrational numbers and their decimals, Gabriel? What do you think must be true about irrational numbers and their decimal expansions?
They do not repeat, but they never stop.
That's absolutely true. Got a pencil? They have decimal expansions that neither repeat nor terminate. They have decimal expansions that neither repeat nor terminate, which makes sense, because if they did repeat, you could multiply them by something that's really big and annoying to get the repeating parts to line up, subtract both sides to get all the repeating parts to go away, divide, and then just turn that into a fraction of integers, right? Just like we were doing before. It's an annoying process, but if it repeats, you can do it. If it terminates, you can way do it. If it's like 4.85987658455, whatever, you just 4 and that many, like 10 millionths, and then 440 whatever million, 10 millionths. Now it's a fraction of integers. So here are the classes of irrational numbers you have to worry about in this class. They come in 3 flavors. The first is imperfect roots. Imperfect roots. Like the square root of 2. If you take the square root of something and you get something nasty, that's going to be an irrational number. If you take the square root of something nice and get something nasty, it's an irrational number. Like negative third roots of 54, right? Like we figured that one out too. Reduced roots as well. 3/8 roots of 10. That would also be irrational. Any imperfect roots are irrational. And you can prove it because of the way that Hippasus did it, right? What Hippasus would do if they said, hey, prove that's irrational, he'd say, okay, so that number is equal to a over b, you cube it, it's a reduced fraction, cube it, so it's negative 54 equals a to the third over b to the third. That's impossible because they can't reduce to 54 because they have no factors in common. And then you get tied to a chair and die. But, well, dunked into a river. That was an important middle step. So any imperfect root is irrational, and Hippasus proved it way before anybody else was willing to accept it. The other one, I heard someone actually say the other one. What is the other one that we're looking at? I heard somebody say it. Nitty? Pi. Multiples of pi. Just in time for Thanksgiving. And I'm actually going to put a little asterisk by this. Multiples of pi. And the reason is because pi is a number that never terminates and never repeats. So we can't do that. We cannot do that process where we eliminate all of those numbers. It actually took forever to prove that this was irrational, but thankfully we've done it. 8 pi, negative pi fifths, 3 pi minus 8. Those are all irrational. Multiples of pi are all irrational with an eye roll and an except. Okay, guys, I know some of you are thinking of dumb multiples of pi that are rational, so let's just get them out in the open. Go ahead. Caitlin. 0 pi is rational. Yes. 0 pi is rational, okay? So there's a multiple of pi that's rational. Next. Next. Go ahead. That's okay. No, wait, that's irrational. That's irrational. That's irrational. Solomon? Well, first you have to raise the e.
Like the I squared, so that it becomes -1.
No, but that'll still be negative pi, right? That'll still be negative pi. Jack? 1. Well, but that's 1 pi. That's irrational. But boo! Yes, indeed, that one for sure. Because it's 0. How about this one, guys? How about pi over pi? Oh, pi over pi. Yeah. Okay, that's rational. Pi minus pi? Okay, yes, fine. That's great. How about pi to the 0? More on that later. Anyway, multiples of pi with an eye roll, except some, are always irrational. Here's the last one. Silly number patterns. Silly number patterns are irrational. For instance, 1.100100010001. Oh, sorry, there was supposed to be another 0 in there. Yeah. That's irrational because it looks like it's repeating, but it's really not. I can't put a bar over anything, right? I can't put a bar over anything. It's just a dumb number pattern. Just a dumb number pattern. How about this one? This is one of my favorites. Negative 0.123456789101112. Well, 1, 3, 1, 5, 1, 4, 1, 5, 1, 6. Yeah, that's irrational, right? Because I can't put a line over anything. That's a different thing altogether. That's a different thing altogether. Well, I squared's rational. Anyway. Okay. Can I get you in 5, 4, 3, 2, 1? You guys are doing well. I appreciate you paying attention, taking this lesson in, and I really do like what you guys are up to today. You can put your pencils down because I actually already made you draw this earlier the year, but I want to show you a Venn diagram of the real numbers. So this box has the real numbers. Every real number, which is pretty much almost every number you've heard of. Some of you guys have heard of something that exists outside of this box, but we'll talk about that. And then we start with the natural numbers, which are just like the counting numbers. 1, 2, 5, 17, whatever, right? These are all natural numbers. And natural numbers are definitely rational because I can write them as 1 over 1, 17 over 1, 10 over 2. I can write natural numbers as a fraction of integers. Then you have your whole numbers, which are the natural numbers, and 0. The natural numbers and 0. 0 is rational because it is 0 over 1, 0 over 10. I can write it as a fraction of integers. Speaking of integers, that's all the numbers. That is the what you call it, like the whole numbers and their opposites. So like -8, -7, -3,279. Those are all also rational numbers because I can write them as a fraction of integers. -8 over 1, -7 over 1, blah, 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 blah. And finally, we have, I'm going to have to use a different tool for this, irrational numbers, which is represented with a double-barred Q, which is like fractions and decimals, like 3/8, -2.8 repeating, 4 and 2/7, whatever. And then you have all the irrational numbers, which live in here, right? All the numbers that live in here, like pi, 3 pi, the square root of 7, 0.010001000001, and so on. Here's something that makes people very uncomfortable. That irrational numbers outnumber rational numbers, and if you do the math, pretty much infinity to 1. Yeah. That not only are there more irrational numbers than there are rational numbers, there are infinitely more irrational numbers than there are rational numbers. Horribly, people often ask, can I get you in 5, 4, 3, 2, 1? Irrational numbers outnumber rational ones so completely that I remember I was in a graduate level math course and one of the students asked, do irrational numbers really exist, or is this just like a fun math game? And the sad truth is, statistically, rational numbers probably don't exist. You make a table, statistically speaking, it will probably never be 4.5 feet long. It will more likely be 4 square roots of 2 long. It'll much more likely be that most numbers are irrational. And then you also have this weird group over here that I'm not going to talk to you about because that's somebody else's fun job. But there's a bunch of stuff that lives outside of the real numbers. That's just like over there. That's just over there. E lives in, E's an irrational number. It lives in here. It lives in here. Hey, I'm not going to steal that thunder. I'm not going to steal that thunder. Guys, that's actually all the time we have. There is a self-assessment tonight. It really is. Is this rational or irrational and why? Put your calculators away, head back to your assigned seat, and I'll dismiss you with the bell.